Welcome to the video for Lecture 14, Section 1. This video is the first of several videos about actuators. In the videos, I will talk about key characteristics of relays, solenoids, solenoid valves, stepping motors, variable speed drives, thermostats, and timers. Before we talk about their characteristics, we need to learn how they are included in the closed-loop block diagram and the overall transfer function for a time-dependent process. Here is the block diagram of our generic closed process. The red circle highlights the actuator, which is going to be described by the transfer function G2. The actuator is different than the other closed-loop process control elements because it has two inputs. One input is PS, which is the output of the controller, G1, which we talked about in our last class. The other input is the manipulated or controlled input. The controlled input can vary depending on the process. For example, for the fluid heater process we talked about in section 4 and 5, the controlled input was the electrical energy used to heat the fluid in our fluid heater. In mixing problems, the controlled input will often be the flow rate of some chemical that is being added to the tank and mixed. In fluid flow problems, the controlled input probably will have some fluid flowing through the tanks. The output of the actuator is labeled as QS. QS describes the amounts of the controlled input that is actually entering the process element. G3. This means that we will think of PS as a control signal which provides information to the actuator, but no material. So PS tells the flow valve how far to open, or it might tell the relay how long to keep the electric heater on to heat the fluid. So be sure to note that there's commonly a units change between PS and QS, because the units associated with QS depends on the controlled input. Here is a list of actuators. In other Lecture 14 videos, which you will hear later, we will talk about them and some of their key characteristics to consider when selecting an actuator to use. You have seen some of these actuators in the labs and will see more. For this class, we will model actuators with a first-order transfer function relating the actuator output QS to the controller input PS. So the transfer function will be kV over tau of V times S plus 1. In many cases, the actuator time constant tau V is very small compared to the other process time constants that we can model the actuator as a constant gain kV. We talked about the gain of a transfer function in section 7 of the course packet. So if we assume tau V, the time constant of the actuator, is much smaller than the time constant of the process, tau P, we can combine and simplify the two elements and use one transfer function that relates the process output, CS, to the controller output, PS. For more details, see page 15-2 of the course packet. One of the things that you need to be able to do is find the actuator gain kV. The problems in this course use both electrical control signals and pneumatic control signals. Newer processes are using electrical and digital control signals, but you may work with equipment that uses pneumatic control signals. Electrical signals usually use current ranging from 4 to 15 milliamperes. Pneumatic control signals are usually air pressure. The ranges vary. In most cases, we will assume that the relation between the input control signal, whether electrical or air pressure, is linearly related to the actuator output. For our first examples, let's assume that we have a valve described by the linear equation given. The expression given is Qm equals 8 times Pa minus 32. So in this example, this is used to express the case that the valve flow goes from 0 to 88 milliliters per second as the input signal goes from 4 to 15 milliamps. So if the control signal is 4 milliamps, the valve has 0 flow, and if the control signal is 15 milliamps, the flow is 88 milliliters per second. Now we are told that the steady state control signal for the process is 8 milliamps. We can use the information to find the steady state flow rate through the valve. In this case, the steady state flow rate, Qs, is 32 milliliters per second. Now we take the difference between the valve equation and the steady state valve equation relating the control signal Pa to the valve flow rate Pm. By taking this difference, we create a difference that we can use to define deviation variables. Using the deviation variable, we find that the flow deviation variable capital Q equals 8 times the control signal deviation variable capital P. We can take the Laplace transform and find that Qs over Ps equals 8. So the valve gain Kv is 8. Sometimes you will be given 2 data points and need to find the linear relation. The 2 points can be used to write 2 equations with 2 unknown, A, the slope, and B, the zero-intercept. In this example, we are given that the flow is 0 cubic meters per second if the pneumatic control signal is 20 kPa, and the flow is 0.001 cubic meters per second when the pneumatic control signal is 100 kPa. We still assume that the relation between the actuator flow rate and the pneumatic control signal is linear, given by Qv equal to A times Pa, which is the control signal pressure plus B. A is the slope and B is the zero-intercept. With the 2 data points, we write 2 equations. Now we have 2 equations with 2 unknowns, A and B. Solving for A and B, we find that A equals 1.25 times 10 to the minus 5 cubic meters per second kilopascal, and B equals a minus 2.5 times 10 to the minus 4 cubic meters per second. So very small numbers. Based on the previous example, you can see that the gain of this valve is 1.25 times 10 to the minus 5. Before we wrap this video, let me remind you again that many actuators will produce a unit change between the input control signal Ps and the actuator output function Qs. For the last example, the control signal was pressure, kilopascals, and the output was flow rates. With relays, you will learn that a small control signal can control a very large electrical input. This means that relays can have very large gain values. This is the end of Lecture 14 Section 1 video. The next video will cover relays. Please write down any questions you have and bring them up in class or lab.